Use the graph to find the horizontal asymptote, if any, of the function. So we're given this graph. It's a picture of a rational function, and we're looking for the horizontal asymptote. So let's understand what a horizontal asymptote is. So for horizontal asymptote, we will have y approaching a number as x approaches infinity or x approaches negative infinity. And whatever that number is that y is approaching is going to be the location of the horizontal asymptote. So y equals whatever that number is. So as we look at our picture, because we're looking for x to be at infinity or negative infinity, we're looking at the ends of the graph. Sometimes we call the horizontal asymptote describing the end behavior. And so we're going to be looking at the ends of the graph where x is approaching infinity and where x is approaching negative infinity. So these are the portions of the graph that will tell me if there's a horizontal asymptote at all and what the value of that horizontal asymptote is. So for there to be a horizontal asymptote, we need y to be approaching a particular number. So let me erase these markings so we can get a better look at this. And what I notice is that this portion of the graph has the y getting closer and closer to the x-axis, and that is to a y of 0. And the same thing happens on the other end of the graph as well. We have the graph getting closer and closer to the x-axis, which is the same thing as the line y equals 0. So because we're approaching a number, a particular number, this graph does have a horizontal asymptote. It has a horizontal asymptote along the line y equals 0. So that may seem a little bit strange looking at the middle of the graph. And we notice that the middle of the graph is crossing that horizontal asymptote at y equals 0. But if we recall the definition again, this definition requires us to be looking at where x is approaching infinity and or x is approaching negative infinity. So what happens towards the middle of the graph has no bearing on what's happening at the ends of the graph. So we do have a horizontal asymptote at y equals 0 for this particular graph. A rancher has 4,584 feet of fencing available to enclose a rectangular area bordering a river. She wants to use part of the fencing to create a partition to separate her cows from her horses by dividing the enclosure into 2 equal areas as shown in the figure to the right. No fencing is required along the river. Let x represent the length of the center partition. And we want to complete parts A through D. For the first part, we want to create a function a of x that describes the total area of the rectangular enclosure as a function of x, where x is the length of the center partition. So we do have a picture. Here's the river, and the rectangular area is this here. And we'll notice that we're only going to be putting up fences along these sides, as the question describes. No fencing is needed along the river. So we need to create this function that describes the area a of x as a function of x, which is marked on the picture. The other information that we're given is that we are going to be using 4,584 feet of fencing. We do want to use all of that fencing because the more fencing we are able to use, the larger area we can create. So I'm going to label this side as X as well because it's a rectangle. It will have the same length as the center partition. And then I'm going to label this side as Y. Maybe I should use a different letter. Let's call it the length. And I'm putting fencing up on these 4 sides. So that's 3 of the X's and that 1 length. And I'm going to use all of the fencing, so if I add these up together, I'll get 4,584. I'm going to solve for the length, and that's subtracting 3x on both sides. That gives the length equals 4,584 minus 3x. And the reason I've done this is that, remember, we're trying to describe the area. And the area of a rectangle is the length times the width. And we have the width of the rectangle here, which is x. And now with that work that I've done here, I was able to write the length in terms of x as well. So we're going to write this as the length, 4,584 minus 3x, times the width, that's x. And I can multiply this out to get 4,584x minus 3x squared. And if I'd like, I can write that in descending order. So that would be 3x squared plus 4,584x. And over here, I've written the variable L inside the parentheses. I should have written the variable x because that's the variable used in the equation. So we have our function that represents the total area of our rectangular enclosure. For the second part, part B, we're going to find the length of the center partition that will yield the maximum area. We want to find the maximum area. Now we just found a function that represents the area, and what I notice about this function is that it is a quadratic function. It's a quadratic function because of this squared. Now with quadratic functions, you can tell the orientation of the graph, which is a parabola, by looking at the leading coefficient. The leading coefficient for this quadratic is -3. And because it's negative, I know that the orientation is down. And when we have a parabola that is down, oriented down, we can tell that the maximum value will occur at the vertex. So I'm going to be able to answer this question about finding the length that yields the maximum area by finding the vertex of this quadratic. Now we have a formula for finding vertex, and this formula will find us the x-coordinate of the vertex. That's -b over 2a. And we have already stated that a is -3, and b is going to be 4,584. So we have -4,584 divided by 2 times -3. That's -4,584 over -6. And with my calculator, I get 764. So this is going to represent the value of the variable that's used in our function, and that happens to be the length of the center partition that we're looking for. So if our center partition is 764 feet, that will yield the maximum area. So in part C, we want to find the length of the side of the fence that is parallel to the river. And I've maybe zoomed out just a little bit too far. So if you'll recall earlier, we found this is the length of the side that is running parallel to the river. These two lines are parallel. This line here is running perpendicular to the river. So we let the side parallel to the river be 4,584 minus 3x. So that length, 4,584 minus 3x, and we found x to be 764, so 4,584 minus 3 times 764. Three times 764 is 2,292. So we're going to do 4,584 minus 2,292, and that gives 2,292. So the length of the side that is parallel to the river will be 2,292. So that will produce the maximum area. So for our final part, we want to know the maximum area. We just found the width that should yield the maximum area and the length that should yield the maximum area. So let's calculate area as length times width. That is 2,292 times 764. And that gives 1,751,088 square feet. So this is the area, the maximum area for our enclosed region, giving us fencing of 4,584 feet. A 16-inch wire is to be cut. One piece is to be bent into the shape of a square, whereas the other piece will be bent into the shape of a rectangle whose length is twice the width. Find the width of the rectangle that will minimize the total area. So we have a lot going on in this question, so let's start by drawing some pictures. So we know that we have this 16-inch piece of wire. That's the length, the total length of the wire. And that piece of wire is going to be bent into the shape of a square. And what we know about squares is that they have all the same sides, all the same length sides. And then we're also told that we're going to have a rectangle. And for the rectangle, the length is twice the width. So if I allow, say, the width to be x, the length will be 2x. And at this moment, I don't know the width of the square, but let's say that that's y. And so what I know is that I'm going to be taking this piece of wire that is 16 inches, and I want to find the minimum area. So let's represent area of these two figures. The area of a square will be the side squared, and the area of the rectangle will be length times width. So for this example, it will be x times 2x. So it'll be 2x squared. Now, I want to be able to use the same variable in both of these because I want to find the total area. And my question here says find the width of the rectangle, so I specifically want to be using the variable x, which is the width of the rectangle. So I want to be able to change this variable of y in terms of x. And I'm going to be able to do that because of the fact that I am starting with this 16 inches of wire and cutting it, so I'll be able to figure out the value of y in terms of x. So what I'm going to use is the perimeter of this square. The perimeter of the square is going to be 4y, and the perimeter of the rectangle is going to be 2 of the 2x's and 2 of the 1x's. So you can see we have 2 of the 2x's and 2 of the 1x's. So that's 4x plus 2x, which is 6x. So because I'm starting off with this 16-inch wire, the perimeter of the square plus the perimeter of the rectangle have to equal that 16 inches that we started with. So I'm going to be able to solve for y. I have 16 equals 4y plus 6x. I'll subtract 6x. That gives 4y equals negative 6x plus 16. And I'll divide by 4. And that gives me negative 3 over 2x plus 4 equals y. So now what I'm able to do is to rewrite the area function here as a function of x instead of y. So let's do that. So this area function, area equals y squared, can now be written as negative 3 over 2x plus 4 squared. And let's simplify this. This is negative 3 over 2x plus 4 times negative 3 over 2x plus 4. Let's multiply it out. This would be positive 9/4 x squared. And if I multiply it, so that's multiplying the first two, and I'll multiply the outside two. That would give me a negative 12 over 2x. I'll multiply the inside two. It gives me a negative 12 over 2x. And I'll multiply the last two, which would give me 16. I have 9 over 4x squared minus 6x plus 16. That's 9 over 4x squared minus 12x plus 16. And now this represents the area of the square. I want to find the width of the rectangle that will minimize the total area. So I need something that represents the total area. I've got the area of the square plus the area of the rectangle. And I've just worked out the area of the square. That's 9/4 x squared minus 12x plus 16. And the area of the rectangle is 2x squared. Let's add those together. So let's write 2x with a denominator of 4. And that would be 8/4. It's the same thing as 2. And we can add those together to get 17/4x squared minus 12x plus 16. So now we have an area function that represents the total area. And remember, our goal is to minimize. We want to minimize that total area. So you can see here that our area function is a quadratic. If we look at the value of a, it's 17/4, which is positive. And when we have a positive value of a, the graph of our quadratic is an up-facing parabola, and the min will occur at the vertex. So I can find the minimum value and the value which it occurs at by finding the vertex. We have a formula for the vertex. The x-coordinate of the vertex h is -b/2a. So this is our value of a, and this is our value of b. We'll do -12 over 2 times 17/4. This is 12 over 34/4. That reduces down to 17/2. I can also multiply by the reciprocal. 12 times 2/17. This is 24/17. And I'm going to type this into my calculator to get an approximation. And that's approximately 1.4. I don't have the directions on the screen right now, but they say to round to the nearest tenth if needed, and I've rounded to the nearest tenth. So let's zoom out and recap for a second here. So this value of 1.4 is the width of the rectangle that will minimize the total area. So this is going to be 1.4 inches. So on our square and rectangle, this width would be 1.4. And if I do 2 times 1.4, that's 2.8. And we also found that for our square, y was -3/2 times x plus 4. So this is going to be approximate. 1.4 times 3 divided by 2. And that should be a negative. Plus 4 gives me about approximately 1.9. So I just wanted to add up the sides here to see if it got close to the 16 inches that we were supposed to have. So 1.9 times 4 sides. The perimeter of that is approximately 7.6. And for the rectangle, we would have 1.4 times 2 plus 2.8 times 2. So that would be about 8.4. So let's see. 7.6 plus 8.4 does give us 16, the 16 inches. Now those are all approximate because I rounded this answer here. So for this question, we're given two equations on the same graph. This one in red that's a straight line is labeled as g of x, and this parabola, which is a curve, is labeled as f of x. And we have a few questions related to this graph. And the first one, part A, is f composed with g of 1. And we're going to use the graph to answer this question. So to find f composed with g, we have to know what this operation of composition means. This operation is exclusive to functions. We haven't seen it before related to numbers. And this operation means that we want to substitute one function inside of another function. Our outside function is the function before the composition symbol, and the inside function is the one after the composition symbol. So I've just rewritten this in an equivalent form with that idea of substituting one function inside of another function. So this is the same thing as f of g of 1. And now that it's written in this format, we can recognize some order to the symbols. Inside the parentheses, we see some symbols that have meaning to us. This is our function notation. We want to evaluate the function g at the value of 1. So we know that x is equal to 1, and we want to find the y. So using the function g, we're going to look for an x value of 1. So all along this vertical line are all ordered pairs with an x of 1. And we want to specifically focus in on this ordered pair because it's on the graph of g, and that y value is 2. So we know that g of 1 is 2. So we can replace that g of 1 with 2. So now we have function notation once again, and we want to evaluate the function f at a value of 2. We know that x is 2, and we're looking for y. So once again, we go to our graph looking for an x value of 2. All of these ordered pairs along this vertical line have an x value of 2, and we're specifically going to focus on this one here, which is on the graph of f, and that has a y value of 0. So f of 2 is 0. So we were able to figure out that f composed with g of 1 is 0. I have another one for us to try. So this will be part B, where we're looking for g composed with f of 1. Let me erase the markings that I had before so we don't get confused by all this notation. And once again, we're using that operation of composition. So we're going to rewrite our function as g of f of 1. On the inside, we recognize the symbols f of 1, and we know that x is equal to 1, and we're looking for y. So on our graph, along this vertical line, has x values of 1, and we're going to focus in on this one here, which has a y value of -1. We focused on that because that's where the graph crosses f. Excuse me, that's where the line crosses f. And so that value, that y value, is -1. So we know that f of 1 is -1. So we can replace f of 1 with -1. And now we're looking for g of -1. If I draw a vertical line where x is equal to -1, you can see this spot here is where it crosses the graph of g at a y value of -2. So g of -1 is -2. So we found that g composed with f of 1 equals 2. So we have several more parts, and the next one, part C, we are finding g composed with g. And we recall that this operation of composition is substituting one function inside of another function. So we'll rewrite this as g of 0. Let me erase my markings. Okay, so I'm going to try not to mark so much this time. We're looking for g of 0, which is right here. G of 0 is 0. And then we simplify again. G of 0 is 0 again. Let's zoom out so we can see all the parts. We're going to do part D, which is f composed with f of 3. We'll start by rewriting this as f of 3. So I'm going to start by looking for f of 3. So I start with an x of 3. I'm looking for where that is on the graph of f, and the y value there is -1. So f of 3 is -1. Then I need to find f of -1. Here's an x of -1. I'm going to find where that x of -1 is on the graph of f, and that is at -9. So f composed with f of 3 is -9. Take a look at part E. For part E, we're going to do f composed with g composed with f of 2. So we have several compositions here, and going from left to right, we'll start on the most outside and then work our way inside. So this will be f of g of f of 2. So first we want to find f of 2. So here's where x is equal to 2, and on the graph of f, that y value is 0. I can replace f of 2 with 0. Then I want to find g of 0. An x value of 0 is here. On the graph of g, that y value is 0, so g of 0 is 0. So I replace g of 0 with 0. And then I want to find f of 0, and that is right here on the graph, and that has a y value of -4. So we found f composed with g composed with f of 2 to be -4. And we finally have one more to go. That's G composed with F. This is part F. G composed with F composed with G of 0. And on this one, we'll rewrite it as G of F of G of 0. And we've already seen a few times that, let me highlight it, that G of 0 is 0. So we're going to replace G of 0 with 0. And we want to find F of 0. And we've seen F of 0 right here is -4. So we can replace F of 0 with -4. And then we need to find G of -4. Here's an X of -4. And we have a Y value of -8. So G of -4 is -8. So we found G composed with F composed with G of 0 to be -8. In this question, we want to use the graph of the basic function and a combination of transformations to sketch the function g of x equals -1/5 absolute value of x minus 1 minus 6. The first thing I want to do is identify the base function, and there should always be a clue in the equation as to what that base function is. So here we have absolute value bars, and that is our clue that we have a base function of absolute value of x. And once we recognize the base function, I want your mind to go to what the graph looks like. We know that the absolute value function has a V-shaped graph, and we notice that this corner here on the graph happens at 0, 0. So that's going to help us understand where we're starting, and we're going to analyze the equation to see what the transformations are, and that will tell us where the graph is going to. So for these transformations, we have several going on here. On the front, I have a -1/5, and I'm going to break this into two parts. We've got the negative and the 1/5. So they cause two different transformations, and that's a multiplying by 1/5, and this is multiplying by a negative. And then we have another transformation of -1, and let's get a different color here. We have another transformation of a -6. So as we look at these, whenever there's adding or subtracting, we have shifts. So this -1 and -6, these are shifts. And shifts can be put into two categories, either vertical or horizontal. All of the vertical transformations happen outside of the base function, and all the horizontal transformations occur inside of the base function. So that -1 is inside of the absolute value, making it a horizontal shift, and the -6 is outside of the absolute value, making it a vertical shift. And then when we focus in even more, there are two types of horizontal shifts. You can shift left or shift right. Because this is a minus, it will shift right. If it were plus, it would have shifted left. And then if we narrow in on the vertical shift, there are two types there. You can have up or down. And the fact that this is minus means that it is down. And if it were plus, we'd be shifting up. So that takes care of the shifts. Another very common transformation is this multiplication by a negative. And when you multiply by a negative, you get a reflection. And there are two types of reflections. You can have a vertical reflection or a horizontal reflection. Vertical, once again, is going to be on the outside. Horizontal is going to be on the inside. So because that negative is outside of the absolute value, this is a vertical reflection. And that means it reflects over the x-axis. So that tells me that instead of our graph being a V, it's going to turn upside down. So let's continue to this last one, the 1/5. So this is one that I don't do very many problems on because they're a little bit harder to notice in the graph. And this type of transformation, when you multiply by a number, is called a stretch or compression. Now, whether it's called a stretch or a compression depends on what type it is, whether it's vertical or horizontal, and also the value of the number. So let's first focus on whether it's vertical or horizontal. So this is going to be vertical because the number is outside of the absolute value. And then when we focus on what that number is, the number is a 1/5. And the fact that that number is a 1/5, which is less than 1, means that this is going to be a compression. A vertical compression by 1/5. So if I kind of strip down and only talk about the vertical compression, let's talk about what this does to the graph. So if I were to think about my starting graph of the absolute value, so thinking of this as absolute value x, and then think about 1/5 absolute value of x, what this does is it takes all of the y values and it brings them down by 1/5. It multiplies them by 1/5. So what ends up happening is every y value gets brought down this way, and you end up getting a graph that looks a little smushed or compressed if you think about it vertically. So if you think about up and down, that graph gets compressed. So let's take a look. When we do these transformations all together, we want to follow a specific order. We're going to start by doing the inside transformations first. So we're going to start with this horizontal shift to the right, and then we'll take care of our reflection and compression. Honestly, it doesn't matter which one of those you do next, and then we'll take care of our shift. So if we were to shift horizontally to the right, our graph starts off looking like this. And if we shift to the right 1 unit, then the graph looks like this. And then if we reflect, the graph will look like this. And then we'll do our compression. Our compression will cause the graph to compress vertically. And what I drew right there is just an estimate. That's not very accurate. If you want me to be more accurate, I can in just a moment. And then finally, we would shift down 6. And so we would get, this is where my corner would happen, and it would be kind of flat looking. And maybe I'll draw this as a solid line since that's our final graph. So this is the picture that I would get from those transformations. Okay, so I'm going to give a little bit more detail on how I came to this decision about whether it was vertical or horizontal, a stretch or compression. So what I've got here is a flow chart that I've created so that we can take a look at the different types. So let's see if I can zoom in on that pretty good. And remember our problem, let's see if I can remember it, was f of x equals -1/5 absolute value of x minus 1 minus 6. So I'm going to be focusing on just this 1/5 here. And when I am deciding whether it is a stretch or a compression, vertical or horizontal, I first want to decide whether it is vertical or horizontal. And all of the vertical transformations occur outside of the base, and all of the horizontal transformations occur inside of the base. So with this 1/5 being outside of the absolute value, I know that it is a vertical, either stretch or compression. So then I'm going to take a look at the value of the number. So the value of the number is either greater than 1 or between 0 and 1. Now we have 1/5, and 1/5 is in between 0 and 1. And so that's why I knew that it was a vertical compression. Now this may be a little bit confusing, but you can see down here that with the horizontal, if we were to look at that, when it's in between 0 and 1, it's a stretch instead of a compression. So if you're trying to memorize this, here's the perspective I take. The vertical stretch and compression will match what your intuition says. Your intuition would say if you're using a large number, a number bigger than 1, then it will stretch the graph out. However, if you're using a small number, a number in between 0 and 1, it will make your graph look smaller or compressed. So these vertical transformations will follow your intuition. However, the horizontal transformations kind of go opposite of your gut, opposite of your intuition. Here we have a number bigger than 1 causing a compression, causing it to get smaller. And here a number in between 0 and 1 causing it to stretch. So that's how I keep it straight in my head, that vertical transformations, you follow your gut. And this also works when you're talking about your shifts up here. You know, here it makes sense that with this vertical shift, -6 makes sense to go down. However, -1 being right goes opposite of your intuition, because on the number line, things that are on the right are positive and things that are on the left are negative. So the shifts are another example of the vertical transformations following your intuition and your horizontal transformations going opposite of your intuition. Okay, so I'm going to continue a little bit more with this question. This question came from a multiple choice question that gave us a few graphs. So I thought I'd talk about for a moment deciding which graph we would choose for this. So if you remember, we're dealing with the function f of x equals -1/5 absolute value of x minus 1 minus 6. So if you'll recall, we found that this graph shifted right 1, down 6. And because it shifts right 1 and down 6, we have a couple that are immediately eliminated. So these two shift up, and they're not valid choices. If we look at the other two choices, both of them have the V shape going down. So that's honoring the correct reflection. Both of them shift to the right 1 and down 6, so they're honoring that transformation. So the difference between these two is really understanding the stretch or compression. In this example, we said it was a vertical compression. So understanding what that does to a graph will help us decide between these two of the choices. So when we have a vertical compression, what I want you to imagine, we have our graph. This is our V-shaped graph. I'm just going back to the original. And you're going to imagine holding at the top and at the bottom and compressing. That's why I've drawn the arrows in this way. You're going to push the top and the bottom together, and what will happen to the graph when you compress it, if you're coming from both sides, it flattens the graph out like this. So with that in mind, you can see that this graph makes more sense with it being a compression. So if this problem instead were f of x equals -5, absolute value of x minus 1 minus 6, then this would be a vertical stretch instead of a vertical compression. So we would imagine our absolute value graph, and vertically we're going to stretch on the top and on the bottom. And what that does is it makes the graph stretch out vertically like this. And so it would make more sense to have this graph if it was a vertical stretch. On this question, we want to use transformations of y equals 1 over x or y equals 1 over x squared to sketch the graph of the rational function. Find all intercepts and the equations of all asymptotes. So by using transformations of these two, this is telling us of our two possible base functions. And looking at the function we're working with, f of x equals 1 over x squared plus 7, we can see that we're going to be using the base function of the x squared since we have x in the denominator and the squared. So we should know what that graph looks like. 1 over x squared is a graph that looks like this. And what we know about this is that the original graph has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. Now we have in our function just one transformation. We have f of x equals 1 over x squared plus 7. So this plus 7 is the one transformation, and it is a vertical shift. We know it's a vertical shift because it's got adding and subtracting, and we're going to go up 7 because it's a plus. And so I'm imagining on this picture here transforming by going up 7. And when I imagine transforming, I'm also going to shift the asymptotes at the same time. So if I were to shift those asymptotes up, the vertical asymptote doesn't change because if you take a vertical line and you shift it up, it's still a vertical line. However, the horizontal asymptote does move from 0 to 7. So we will now have a horizontal asymptote at y equals 7. And then we can sketch the graph to be like this. So it's the same graph as the original, just shifted up by 7 units. In addition, this question is also asking to find any intercepts. You can see by our picture that the graph will never cross the x-axis and it will never cross the y-axis. So there are no intercepts for this particular example. Thank you for checking out my videos. Have a great day.